Welcome. This talk is about the CallGraph abstraction provided by NOELLE. This talk is for my class Advanced Topics in Compilers that I teach at Northwestern University. I've decided to open these talks to everyone, even if they're not professionally made, with the hope they will be useful for anyone interested in doing compiler research while taking advantage of the NOELLE framework. So this talk is organized in three parts. First, I'm going to refresh our memory about the CallGraph abstraction provided by LLVM. This is part of what I teach in the class 323, Code Analysis and Transformation. And then we're going to go to the different abstraction with the same name called CallGraph that now NOELLE provides, and why do we need a different implementation of it. And finally, we're going to look at other abstractions that are built upon the CallGraph that provided by NOELLE. First of all, the CallGraph. Why do we need it? A CallGraph answers the question, which procedure can invoke which other procedure? Or in other words, if I have a function, what are the other functions that can invoke this function that I have in front of me? This is especially difficult to answer this question in higher order languages, where where functions are values. But it's also difficult for C programs. Even in C programs, you can invoke a function indirectly via pointer. So think about, to understand how to compute the CallGraph that is complete. So I want to know what are the possible functions that these indirect call in C can invoke. I need to fundamentally understand the aliases between pointers, which relies on alias analysis, which etc. etc. So for now, let's ignore this indirection or indirect calls. And we're going to come back to it later on this talk. But for now, let's assume we have only direct calls. So there is no ambiguity about which function a given call can invoke. This is called static CallGraph. Now, in this static CallGraph, we have a graph where we have nodes that are function and edges that represent which function can invoke which other function. So this is an example. If I have on the left this code where f invokes g twice and then invokes h, g invoke h invoke f and I doesn't invoke anyone, then the typical CallGraph that you have, this is an example, this is what LLVM CallGraph will provide you, is this graph where you have one edge per call instruction. So the fact that f invoke g twice means that it leads to have two edges from f to g. Now, if you want to obtain this abstraction as described in the previous slide with using while using LLVM, then you need to use the pass CallGraph wrapping pass, which so in your own pass, LLVM pass, you have to declare your dependence with that pass, with the CallGraph wrapper pass, and then you can fetch the CallGraph as described in the previous slide using this API. What are the limitations that the CallGraph provided by LLVM has, and why do we need that different implementation? So there are two problems with the CallGraph provided by LLVM. The first one is, if the callee is unknown, so in other words, I have an indirect call and I don't know, I cannot determine statically a single function that this indirect call can invoke, then the CallGraph abstraction of LLVM provides no edges in the CallGraph that capture this unknown. This creates ambiguity. Because if I have a node in the CallGraph that has no edges that go out, no outgoing edges from it, you don't know whether this is because indeed this function cannot invoke anyone, or you just don't know what are the possible functions that this function could invoke indirectly. You cannot distinguish these two very different scenarios by only using the CallGraph abstraction. Also, if I have an indirect call and I do know what are my possible callees, let's say I come from an object-oriented programming language and yes, I have a virtual call, but so I don't have a single function I could invoke, but I have a very strict number of possibilities. in the code, these possibilities are not expressed in the CallGraph provided by LLVM. So in particular, if there is more than one possible callee, then there is no edge in the CallGraph. In other words, the CallGraph provided by LLVM, while being good, is not complete, which block optimizations. That's why we need, in NOELLE, we provide an alternative implementation of the CallGraph abstraction. So we call this program CallGraph. And this is to emphasize that it's a CallGraph that is about the whole program and is complete and conservative. So in other words, the lack of an edge implies only one semantic. It means that you cannot invoke the potentially destination of the function that you don't have an edge to from the source of that hypothetical edge that doesn't exist. So in other words, if there is no edge between f and g, it means f cannot invoke g. And if there are n possible callees from a given indirect call, all of them are expressed explicitly as outgoing edges. The graph is hierarchical, and we're going to see how. But first, let's compute the program call graph. As usual, you're using NOELLE, therefore you first have to normalize your code. If you don't know what that means, please watch the Introduction to NOELLE talk. Now that you have normalized the code, you can ask NOELLE to compute the program call graph. In order to do that, you first, of course, have to fetch NOELLE from your pass. And then you need to fetch the functions manager, which is the manager about functions. And that manager has the capability to compute the program call graph. And you can do that by invoking the API get program call graph. Now the return is an object of the class NOELLE call graph, or the class call graph in the namespace NOELLE. How you can use the program call graph? So first of all, you can iterate over every node if you want. So by invoking this API, you iterate over every node of the program call graph. And every node is an instance of the class CallGraph function node, which represents a node of the graph. From here, you can retrieve the function that this node represents with the function, with the API get function. And now you have the LLVM function, so you can use all API of LLVM to see if it is a declaration function, so it's an empty body, or if there's a body. Also, from a node, you can iterate over outgoing edges. So you can see what are all possible callees that you can invoke from that node. And then you can iterate over the edges. And this each edge is of the class, is an instance of the class CallGraph function edge. I know it's not a great name. I'm really bad at giving names, but this represents the fact that this is an edge between a function and a function. Okay. Now, from this edge, you can retrieve the destination of the edge with the API get callee. And now you have a node of the graph of the PCG that is a function that represents a function that can be invoked from the function represented by the object node. And as such, you can use all APIs of that node, including the one we have already seen, get function, to get the LLVM function. Another way to use the PCG, the program call graph, is to go from an LLVM function to the node that represents that function, okay, in the PCG. Each edge in the program call graph can be either may or must. And the specific semantics of those is the following. A must edge means the following. When the related call instruction that has created this edge executes, the destination of that specific edge is guaranteed to execute. A may instead means when the related call instruction that has created that edge execute, the destination of that specific edge may execute. There is no guarantee. In other words, if a given call instruction has only one possible callee, then that edge, then that call will create a masked edge. But when instead a call instruction could have 3, let's say, callees or more than one callee, then all of these edges, then we're gonna create one edge per callee, and all of these edges are may edge. And when you have an edge, to see if it is a may or a must, you can just invoke the API is a must call. The program call graph of NOELLE is hierarchical. What this means is the following. If you have a function f that invokes g n times, the PCG of NOELLE includes only one edge from f to g. Only one, not n. The source of that edge is f, and the destination of that edge is g. However, that edge includes n sub-edges, one per call. And now the sub-edge is of a different type. It relates the specific call instruction of f that invokes g. So the source of that sub-edge is a call instruction, and is a call instruction of f. The destination of that sub-edge is the function g. Let's assume that you have an edge of type CallGraph function edge, which is a binary relation between two functions. Then from here, you can query it to get all the sub-edges. You're gonna have at least one, but you can have more than one. And if you have more calls that connect the source function to the destination function. And then each of sub-edge is of type CallGraph instruction function edge to represent the fact that that edge is a binary relation from an instruction and a function. And then, of course, this is an edge, therefore you can check if this edge is a may or a must. And if from a sub-edge you invoke getCaller or getCallee, you're gonna get the object that represents the caller or the callee. The caller is gonna be the source of the edge, which is an instruction of the function. And the abstraction that wrap the instruction of the caller that has invoked or could invoke the callee is of type CallGraph instruction node. This is different than CallGraph function node, which is the source of the edge, not of the sub-edge. And then from the sub-edge, you can even query to get the instruction. Now let's look at what are the other abstractions that we build upon the program CallGraph that NOELLE provides. The first abstraction is island. An island is a disconnected subgraph of a graph. So an island in the PCG is a set of functions that cannot be reached from any other function of another island. So from the program CallGraph, you can retrieve the islands of that graph by invoking the API getIslands. Now that you have the islands is the abstraction is basically a map from a function to its own island. So if you pass a function, an LDN function as input to the islands, you get back the island that includes the function you give as input. So in this case, for example, we can iterate over the functions, get the island of every function, and check if the island of the function is the same island of the function that includes main. And if it isn't, if a given function belongs to a different island, you know that that function cannot be reached from the main function of the program. Another abstraction is the strongly connected component called Acyclic graph. This is the strongly connected component direct acyclic graph of the program CallGraph. We give a different name to emphasize that it's coming from the program CallGraph. So from the program CallGraph, you can invoke get SCCCAG. It's a mouthful name, I know. And return the object that represent the strongly connected component direct acyclic graph of the program CallGraph. And from here, you can use it to understand whether a function belongs to an SCC or not. So in other words, like a recursion. So to do this, you fetch the node of the program called graph that represents a given function, like using the previous API we have already seen. And then from that node, you can use the SCCCAG object and using the API get node to retrieve the SCC that, or the nodes of the SCCCAG object that the input node belongs to. And if what it returns it's indeed an SCC, then you know that that function belongs to a recursion. With this, thank you for listening, and I hope this talk will help you.